short video we are going to be looking at another combinational circuit, the demultiplexer. Now if you are aware of what a multiplexer is, then this is going to be something very easy to understand, because a demultiplexer is just the opposite of a multiplexer. It performs the opposite function. Now in a multiplexer we would have noticed we have 2 power n inputs, n selection lines and 1 output. As you can see here, a demultiplexer is the exact opposite. 1 input, 2 power n outputs, and the n selection lines remain the same. So what is this circuit doing? We are giving it one input, and that input is going to be exactly reflected in one of the output lines. All other output lines are going to be 0. But again I have 2 power n output lines. Which output line am I going to select to reflect the input? So that selection question is where our selection lines come into play. Again, n selection lines can represent 2 power n combinations. This time each combination represents an output line. For example, if I have, let's say, 4 output lines and 2 selection lines S0, S1. My selection lines can take the combinations 0, 0, 0, 1, 1, 0, 1, 1, and each of these represents one output line, O0, O1, O2 and O3. So if my selection lines are taking the value, let's say 1, 1, then whatever input D I am giving will be reflected in O3 and all others will be 0, and so on so forth. That is the broad overview of a demultiplexer. Now we will again quickly see how a demultiplexer is constructed. I am going to take the simple example where you have one input called D, 2 selection lines S0 and S1, and 4 output lines which I am going to call here Y0, Y1, Y2 and Y3. Now as in any combinational circuit, we start by drawing our truth table. So S0 and S1, these are the combinations it can take, and in each case which output line is going to reflect my input. That's what I have written here. So if my selection lines are 0, 0, Y0 is going to reflect D and all other 3 are going to be 0. If it's 0, 1, Y1 will reflect D and so on. So this is the basic information given to us from which we need to construct a circuit diagram. So we have here our lines S0, S1 and D, and let's also include the lines S0 complement and S1 complement, because we might need them somewhere in our circuit construction. Now if you have watched the video pertaining to multiplexers, or if you are aware of how a multiplexer is constructed, you will know that we figure out a logical expression involving some form of S0, S1 and D, such that when we have the combination 0, 0, that expression should evaluate to D, and in all other cases that expression should evaluate to 0. Similarly for 0, 1, 1, 0 and 1, 1. So, and how is this generally done? You go back to this truth table. Wherever you have a 0, you replace it with S0 complement, and wherever you have a 1, you replace it with S0. Similarly here, if you have a 0, you replace it with S1 complement. If you have a 1, we will replace it with S1. So when I do this on paper and show you guys an example, it will be better to understand. So here we have S0 taking 0 and S1 also taking 0. So we will take S0 dash S1 dash D. This will be S0 dash S1 dash D. Now if you this is S, I'm sorry. So if you calculate the different possible combinations of values this expression can take, you will notice that when your S0, S1 are both 0, this final expression is going to give you D, and in any other case it will be a 0, which is exactly what we want. When my S0 and S1 are both 0, I want my output Y0 to be equal to D, and in all other cases I want it to be equal to 0. So I think it would be fair to call this line Y0. And if things are not making sense to you, again I would urge you to pause the video and to draw a truth table for this expression and understand that when S0 and S1 are 0, your output will be equal to D, and for any other combination of S0 and S1 you will get a 0. Similarly for S0 0 and S1 1, the expression must be S0 dash S1 D. Let's try that out. S0 dash S1 D. Connect. And this you will find for this combination your output will be a D, and for all other combinations it will be a 0. So this is what I expect from my y1 line, so I'll label this y1. Similarly here it must be S0 S1 dash D, S0 S1 dash D, which will be y2, and S0 S1 D should be my y3. Now I am rushing through this quickly because if you are familiar with multiplexer, which you are expected to be before coming to demultiplexer, this should be making sense to you. But if for some reason you're not very clear, I would urge you to revisit multiplexers first and then to try out these truth tables, as I already said. So coming back, we have S0 S1 D, which is y3. So this again is S0 dash S1 D, S0 S1 dash D, S0 S1 D. So you will notice here that each of these gates, and you see we've developed 4 output lines. Now in your multiplexer we did something similar to this, but in the end we connected all of them to an OR gate. That is because ultimately we need only one output, but here we need 4 output lines which we've got already, so we're not going to do any further connecting. This is our input, these are the selection lines, and these are the outputs. This is our demux. The circuit is over. Now if you try each of these, you will see that if I take the combination 0 0, this one will give me a D and all others will give me a 0, and similarly for the other corresponding combinations. So that is a broad overview of how a demux works. One input, n selection lines, and 2 power n output lines.